Algebraic vectors in R2. Express the free vector from A 2, 3 to B minus 3, 4 in ordered pair notation and determine its magnitude and direction. So we have two positions, 2 points rather, which are 2, 3 and minus 3, 4. So let's say this is our point 2 and 3, then minus 3, 4 will be kind of on the left side. So the vector could be like this. So let's draw this vector here and say this is the point A, which is 2, 3, and this is the point B, which is minus 3, 4. And what we need to find is, this is a free vector. Free vector since the tail is within a coordinate plane but not at the origin. Now, express the free vector in ordered pair notation and determine its magnitude and direction. So ordered pair notation is within parentheses. So let the vector be, let's say A be the vector which should be AB, A to B, right? And this we can write B minus A. So we'll find the difference of components of x and y and get our vector. So the components difference is minus 3 minus 2, and the y difference is 4 minus 3, 4 minus 3. So we get this equal to minus 3 minus 2 is minus 5 and 4 minus 3 is 1. So that becomes a vector from A to B in ordered pair notation. So that is how we write. Here this is x component and 1 in this case is the y component. The second part of this problem is determine its magnitude and direction. So magnitude of this vector A is equals to square root of x square plus y square, right? The x component and the y component squares should be added and then we square root it. So we get square root of 25 plus 1, which is 26. So it is square root of 26. Now the other part is to find its direction. Now to find the direction, think like this. We have this vector here. So the direction is normally given with the positive x-axis, right? Now there are different ways to give direction. We could give direction from the west side also, right? So either way, so what we will do is to find the direction. Now we know the component. Now once we know the component, what we can do, we can plot the vector as a position vector. So let me show you that part. So we'll draw a position vector to represent vector A or vector AB. When we're drawing a position vector, we will be putting the tail at the origin, and then that coordinate point becomes the head of our vector, minus 5, 1. So minus 5, 1 will be something like this, right? Let's say this point is minus 5 for us. So this is the position vector A. And the point given here is minus 5, 1. So this is minus 5 and the y point will be 1, right? Now from here we can find tan theta. Let this angle be theta, correct? So what is tan theta equals to? The acute angle theta for us will be 1 over 5. Let's consider acute angle theta here first. And therefore theta equals to tan inverse of 1 over 5. So you can use the calculator to calculate the answer. So we get second function tan inverse within bracket 1 divided by 5 bracket close equal to 11.30. So we get an angle of 11.30 degrees. Now it is customary to write this angle as a principal angle from positive x-axis, right? So that is one way of writing. So from positive x-axis we say the angle of the vector with positive x-axis is, so let's say this angle is alpha. So we say the angle or the direction in which it is going from positive x-axis counterclockwise is alpha equals to 180 degrees minus 11.30, and that gives us 168.7 degrees. So that is one way of saying it. The other way is, we know this is 11.3 for us. We can write down the angle from north, we can write down the angle from west. So these are different ways of writing the answer. Or we can provide bearing angle, right? Which will be 270 plus 11.3. So we can write all those different ways. We can represent the answer in all those different ways, right? But normally, in coordinate planes, we'll be writing our angle from positive x-axis. So that's a preferred answer, right? So we'll say the direction of the vector is 168.7 degrees from positive x-axis. Thank you.